The AI Hippocampus. How far are we from human memory? By Zixia Jia and the team at BIAI Peking University.
Yeah, and we're diving straight in today. This paper is, it's a beast.
It really is. It basically says, look, we need to stop just obsessing over bigger context windows and start actually engineering a memory architecture.
One that's analogous to the human brain. And they give us this amazing three-part taxonomy to think about it.
First up is implicit memory. That's the neocortex, all the knowledge that's baked right into the model's weights.
Then you have explicit memory, which they call the hippocampus. That's your external storage array, vector DBs, all that good stuff.
And finally, agentic memory, the prefrontal cortex. This is the working memory that lets an agent actually plan and use tools over time.
And that framework is, I think, the perfect way to understand the whole engineering stack for fixing things like hallucination and context limits.
Okay, so let's peel that back layer by layer. Let's start with the digital neocortex, implicit memory.
Right. We usually just call this the model, right? The parameters.
Exactly. But the paper wants us to see it not just as a processor, but as a storage device. It's all about parametric knowledge.
And they get into this really fascinating, super technical finding about how transformers actually store facts.
Yeah, the feed-forward networks, the FFNs, are basically acting as key value memories.
It kind of blew my mind, too. We always think attention is the star of the show.
Right, the thing that connects all the words.
But this suggests the FFNs are where the facts actually live. You can think of them as this huge associative map. The key is a concept like the Eiffel Tower.
And the value is the output, like Paris.
Exactly. It's like a giant hash map, just implemented in neural weights.
So there are literally specific neurons that fire for specific facts. They even mention this idea of knowledge neurons.
They do, yeah. The idea that you can find the one neuron responsible for knowing who the first U.S. president was, and if you shut it down,
the model just forgets.
Wow.
Which is amazing for interpretability, but it leads to a massive engineering headache, which the paper really focuses on.
Editing. It's the biggest bottleneck for this kind of memory. In a normal database, you just run an update command. It's easy.
But you can't just control F a 70 billion parameter model.
No way. The paper dives into these crazy techniques like roam and memit. They're trying to find the causal trace of a fact.
The path of activation.
Right, and then mathematically intervene to swap it out. It's like performing brain surgery to change a single memory.
But even that has its limits. They talk about this trade-off between adding new information like with Laurier and unlearning.
Unlearning is huge, especially for safety. You need to scrub private data or toxic stuff. But because it's all associative...
You pull one thread and the whole sweater unravels.
Pretty much. That's catastrophic forgetting. You try to make it forget one bad thing, and suddenly it's worse at a completely unrelated task.
And speaking of unraveling, the paper drops a pretty hard truth about scaling laws.
Yeah, this isn't the bigger is better scaling law we're used to. This is about knowledge capacity.
It's a negative exponential relationship.
Right. Exactly. You just can't cram all of Wikipedia or Wikidata into the parameters efficiently. The model starts to struggle. It is mathematically impossible to memorize everything in the weights alone.
Okay, so the neocortex has a hard cap, and it's a nightmare to edit, which is the perfect segue to the second part of the brain.
The hippocampus.
We need a separate system for the details. This is explicit memory.
Or as everyone in the industry calls it, RAG, Retrieval-Augmented Generation.
But the paper argues that just, chunking text and throwing it in a vector database isn't going to cut it.
Not for complex reasoning, no. They break down the different ways to represent the data. Vector embeddings are great, they're fast, scalable.
But they miss the relationships between things.
They're terrible for structural reasoning. A vector search can't really answer how is the director of movie A connected to the composer of movie B. The concepts are too far apart semantically.
And that's where graph representations come in. They mention something called Hipporag.
Yeah, Hipporag is a great example. It runs an algorithm kind of like PageRank on a knowledge graph to find paths between nodes.
So it's performing multi-hop reasoning.
Exactly. It retrieves a whole subgraph of connected ideas, not just the most similar sounding text chunk.
This really feels like where the engineering comes in. It's not just about the LLM anymore, it's the whole architecture around it.
That's a crucial point. Most people just freeze a model and slap a database on top. The paper calls that training-free RAG.
But there are better ways, like retro.
Right, the Retrieval-Enhanced Transformer. With retro, you actually pre-train the model with the retrieval system in the loop. The model learns how to use its external memory from day one.
So it's not just, here's some context, good luck. The model was basically raised knowing it had a library card.
That's a perfect analogy. And then you have other approaches like replug, which is clever. It keeps the LLM frozen, but it trains the retriever to find documents that the LLM seems to like.
It creates a feedback loop.
Yep. Now, I want to get your take on the long context debate. We've got models with million token windows now. Does that just kill the need for this whole AI hippocampus?
Does the context window just eat the database?
The paper argues no, and for two big reasons. The first is just cost attention is computationally expensive, but the second is the lost in the middle problem.
Right. Models tend to forget things you put in the middle of a giant prompt.
And that's where systems like MemTRM or LongMem come in. They decouple the memory from the main model.
How does that help?
Well, LongMem uses a separate, smaller memory encoder. It's more efficient than raw attention. It's designed to solve that attention dilution problem so you don't lose the stuff in the middle.
So you're offloading the memory task.
Yeah.
You don't hold your whole life in your working memory. You retrieve it when you need it.
Precisely. Which brings us to the third layer, because having knowledge and having facts is useless if you don't know what to do with them.
The executive function, the boss, the prefrontal cortex.
Or agentic memory. This is where we go from a chatbot to a true agent, something that can plan and act over time.
And for an agent, memory is broken into short-term and long-term. Short-term is just the context window, right?
Yeah, what just happened? But long-term memory for an agent is different from RAG. It's not world knowledge.
It's the agent's own history.
It's the trajectory. User preferences, past actions, past mistakes. It's episodic memory about its own life.
This is where they bring up the concept of reflection, which I love.
Frameworks like reflection, yeah. It's a feedback loop where the agent literally reviews its own actions to generate new insights.
So it fails at a task and then writes itself a little note saying, hey, don't use that tool for that file type next time.
It's writing its own heuristics. That's agentic memory. It's not just storing facts, it's storing wisdom.
And the paper explicitly mentions the stack that's evolving to do this. LangChain, Lamy Index, and especially MemGPT.
MemGT is the perfect example of this. It treats the context window like an operating system treats RAM. It has a paging mechanism. Paging, like in a real computer.
Exactly. It decides what information is critical to keep in the active context and what it can page out to long-term storage, all on its own. It's memory management for thoughts.
So how do we even know if this stuff is working? They mentioned some benchmarks. What was it, MQuake?
MQuake is really cool. It tests multi-hop editing. So say the model knows the U.S. president is Joe Biden, and therefore the first lady is Jill Biden.
Okay.
Now, you edit the memory to say the president is now Bob. Then you ask, who is the first lady?
It should say Bob's wife, not Jill Biden. It needs to understand the consequence of the change.
Exactly. If it still says Jill Biden, it failed the test. The reasoning didn't propagate. And you also have simpler things, like can the agent remember something from 50 turns ago?
Or does it fall apart if you change one word in the history? Perturbation tests.
Right. Robustness is the key metric here.
Okay, this all makes sense for text. But the paper points out a huge bottleneck, multimodality. And video is the killer. They call it the temporal problem. An image is static, but a video unfolds over time. An agent needs to remember what happened 5 seconds ago to understand what's happening now.
And then there's the visual token explosion.
Ugh, yeah. If you tokenize a video frame by frame, you just flood the context window instantly. It's unmanageable.
So what's the fix? They mentioned something called MEMVite.
Memory-augmented vision transformers. The idea is to cache representations. Instead of storing every pixel of every frame, it stores a compressed summary of past frames.
So it doesn't have to reprocess the whole scene over and over.
Exactly. It compresses a visual memory so the agent can keep a long-term understanding like tracking an object without melting the GPU.
It's like how we don't remember every photon that hits our retina. We just remember the scene. We compress it.
We compress it into concepts, and that's really the core argument of the entire paper, moving from raw data to semantic retention.
So to bring it all together, the paper's big conclusion is this unified view. You can't just think about these three memory systems in isolation.
No, in a functioning system, they're all integrated. The agent queries the RAG system to augment the knowledge in its weights. It's a constant loop.
And the ultimate goal they point to is this self-evolving agent. That sounds pretty formidable.
It's the holy grail. An agent that doesn't just retrieve data, but actually updates its own parameters or its memory structures based on experience. It becomes a true continuous learner.
You know, that leads me to a kind of provocative thought. If we perfect this agentic memory system, this robust external brain, do we solve catastrophic engine? Forgetting just by, well, giving up on the neural network part.
What do you mean?
I mean, if the weights just become a frozen reasoning engine, a really good CPU for logic, and all the actual learning and remembering happens in the external architecture and the vector stores and knowledge graphs, are we even building brains anymore? Or are we just building really advanced filing cabinets attached to a CPU?
That is the philosophical question of the decade, isn't it? The paper would argue you need both. You need the intuition from the weights, that's your common sense, but you also need the precise recall of the filing cabinet. A filing cabinet can't write a poem about its contents.
And a CPU can't feel nostalgia.
Right. But a system where all three, implicit, explicit, and agentic memory, are working in concert, that starts to look a whole lot like something that can observe, reflect, and evolve.
The AI Hippocampus, a paper that really makes you think about the architecture of intelligence itself.
Absolutely. It's a blueprint for what's coming next.
Thanks for listening to AI Paper Podcasts. If you want to dive deeper, the link to the paper is in the show notes. We'll catch you on the next deep dive.